Morning. Okay, welcome back, folks. It is the Ides of March, right? It's March 15th. Okay. All right. So here's where we are. And thank you for your patience regarding the homework grading. It's gone very slowly. I've just finished a batch, and your homework ones are coming next. Okay. So yeah, I never know what's going to come up, but your homework one is up next as the next homework batch. Now, again, as a reminder, we're sticking to schedule. Lessons 11 through 18. That's going to be due Tuesday of next week. So Tuesday, March 23rd. All right. Lessons 11 through 18, part 2 of the class. We're going to cover lesson 18 a day on binomials. That's a key topic. All right. And we're going to have a lot of fun today. We're going to play some games today. All right. And then we're going to discuss the homework on both St. Patrick's Day on Wednesday the 17th and then next Monday the 22nd. Homework due the following day. All right. And hope I'll get that homework one batch done soon. I just finished a previous batch. So, all right. Any questions thus far? Any questions thus far before we start with the videos? I might go back and forth between various pieces. All right. So let's start. All right. Questions in chat. We're recording. All right.
Hi, everyone. Let's start lesson 18 on binomial distributions. How many successes and what are the chances? Actually, we're going to start this with a fun game. It's the Monty Hall problem, which comes from a famous game show from 40, 50 years ago. Here's Michael, our old friend Michael from Ding, to explain.
And in fact, I might have better resolution on this. Hold on. I'm going to get a better thing here. Yeah. Okay.
Yes, most people decided not to switch.
Okay, so let's actually play this game for ourselves. This is a great applet from Rossman and Chance. Let's drag this down here. So let's actually play this game. I'll do a couple of rounds and then you'll go ahead and play 18 of them on your own. Okay, so let's say that I want to pick door number 1. I just sense, my spidey sense says that the money or the car is behind this door. It's a car. That's the grand prize, I'm hoping. So let's open this door. Well, it doesn't open the door for me right now, unfortunately. But what the game show host does, Monty Hall, he opens another door, which is this goat over here. We reveal a goat. Now, the idea is that I can either stay with my current door, door number 1, or I can switch over to this third door, door number 3. So let's say that we always employ a strategy of switching. We're going to play that game. We're going to employ a strategy of switching. So instead of staying on door number 1, I'm going to open up door number 3. Switch, and I win the car. And you can see that I register the win, and you see that dot there. I've won 100% of the time thus far. Let's try this again. Play again. All right, this time my spidey sensed that the car is behind door number 2. Open that, okay? And Monty Hall reveals to me that a goat is behind door number 3. Looks like kind of a satanic goat, huh? All right, so once again, I have a choice to either stay behind door number 2, or I can switch over to door number 1. Okay, I'll go ahead and switch to door number 1, and once again, I win the car. I'm 2 for 2, and that's registered over here. So here's what I'm going to do. I'm going to email this link to you, this Rossman Chance applet, and go ahead and play 18 rounds. Play this 18 times, and you can pick whatever door you want at first, but promise me that when given the choice, you'll always make the choice to switch to the other door, like I did. So let's go ahead and stop here, and you play 18 rounds of this game, and let's see what proportion of the time you win and what proportion of the time you lose. Is it really 1/2, 1/2? So go ahead and play 18 rounds of this and then come back to me at the next video.
All right. So instead of emailing it to you, I'll just put it in chat. Okay. In fact, I put it in chat earlier. I'm just going to grab it from the chat. Okay. So open up this link, and that should give you the website I just showed you, assuming you're connected to a web browser and all that good stuff, right? So click on that. Okay, so I posted that link. Click on that, and you should see. Yeah, you should see this, right? Play 18 games of this. All right, 18 rounds. Remember, you click this for play again. Always switch. All right. Always employ the strategy of switching and see how often you win. Is it really 50-50? Is it really going to be 50%? Try it. I'll give you a few minutes. And then tell me how many times you win out of the 15 here. So put in chat how many times you win under the switching strategy. You're always going to switch. Out of the 18 rounds, is it going to be close to 9? We see a bunch of numbers close to 9 or half. 18 rounds. After you finish 18 rounds, tell me the number of times you won with the switching strategy. I'll give you a couple minutes. Wow, 6 wins and 12 losses. That's unusual, but I'm glad that we got people with unusual results. That'll happen sometimes. So look at these numbers we're getting. Do they seem to be centered around 9 or half? What do you think? So far, we're seeing a 12, a 13, 9, 11, 12, 15, 12, 6, 10, 11, 11. 11, okay. 13. Huh, do these seem to be centered around 9? What do you think? And go ahead and keep playing. I mean, even if I start talking again, go ahead and keep playing. 12. You're commenting, you're seeing about 10 and 11. Yeah. Okay, about 10 more seconds. Keep playing, but 13. All right. Take a look at these numbers. Does it seem like they're centered around 9? And yeah, you can talk about mean, median, and all that stuff, but mode. But what do you think? I mean, do you think it's half-half? Look at the numbers we're getting. Does it look like the probability of winning under a switch is 1/2? It looks more like what, right? Think about that. Let's go on to the next video. Keep commenting in chat. Go ahead and talk about it and why that is. Okay, let's go on. We're recording, right? Okay.
Hey everyone, I hope you've played your 18 rounds of the Monty Hall game with switching. A quick recap. So let's say that I think the car is behind door number 1. Monty Hall decides to open door number 3. He gives me a choice to either stay behind door number 1 or switch to door number 2. As for the strategy that I told you to use, we must switch to door number 2. In this case, I lose, and that registers a loss over here. Okay, let's try this all again. Let's repeat the switching strategy 18 times. This is going to be like the movie War Games, where it's all very fast.
I didn't want you to do this.
Huh, look at that. So I've won 56% of the time, and I've lost 44% of the time. Let's try it again. After now 36 rounds, hey, it looks like I've won 2/3 of the time. And guess what? According to probability, I'm supposed to win 2/3 of the time. If you switch, there's a 2 in 3 chance that you're going to win the car. Let's have our old friend Michael explain.
So I'm going to go back to the pure video because the reception's better on that. Plus, let's do the whole copy.
Chance of winning if you switch. By the way, this problem was famously featured in the film 21, Kevin Spacey there, explaining the Monty Hall problem. So it's a very famous problem. Now, what does this all have to do with today's lesson? We'll see in the next video.
Okay, so I can email that clip on 21. Kevin Spacey describes it.
Stream 85 plus live channels with no hidden.
Okay, so let me, so I put these videos in the playlist. I'm going to go straight to here.
Lesson 18 on binomial distributions. So it turns out that the Monty Hall problem that we talked about is deeply involved with these binomial distributions. Let's take a look here. So let's say that X, this random variable, represents the number of wins among the 18 rounds played under the switching strategy. Then X has as its distribution a binomial distribution, BIN, where the number of rounds or trials is 18, and the success probability per trial, P, is 2/3. 2/3 is the probability that you win the car under the switching strategy for any given round. Okay, so this is a distribution, all right? So X is a random variable that can take on a value between 0 and 18. If you play 18 rounds of this game, then you can win the car between 0 times and 18 times. X can take on various values between 0 and 18. Now, the binomial distribution involves these possible values of X and their corresponding probabilities. Now, there's almost no chance that you win the car no times or 1 time or 2 times, for example. The most likely number of wins is, look at this, 12 out of 18. That's one reason why I chose 18 rounds. 2/3 of 18 is 12. It turns out that this is the mean for this distribution. Now, the probability that you win the car 12 times out of 18 under the switching strategy is about 20%, 0.196, and it's the highest probability of all of these. So it's not surprising that 12 is the most likely number because 2/3 is the success probability. 12 is 2/3 of 18. So this is the probability distribution for X, the number of wins out of 18 rounds. It's almost 0 over here. Then it goes up, 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 and it peaks at 12 wins out of 18 rounds, then down, 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 and it's very unlikely that you win the car all the time. Of course, these probabilities add up to 1, give or take rounding error. Now, actually, we saw this in practice, at least I did. In 5 of my statistics classes, 101 pairs or teams of students played this Monty Hall game. They played 18 rounds of this game, and they recorded the number of times that the student contestant won the car out of the 18 times. For each pair, the contestant was one student and Monty Hall was the other student. So, based on the 101 teams, no team saw these numbers of wins for the car, 6 or fewer. Nobody saw 6 or fewer wins in this switching strategy. But as a matter of relative frequency, it went up, 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 up. This time it peaked at 11, but 12 was also pretty high over here. But you saw the highest relative frequencies for basically 11, 12, 13 wins out of 18. Now, as you see, the relative frequencies that I actually observed in my 5 classes, they did not match the theoretical probabilities perfectly, but they were pretty close. They were pretty close. And again, we saw a peak at around 2/3 of the 18 rounds, about 12 or 13. Okay, so we're seeing the binomial probabilities playing out in these relative frequencies. And I can guarantee you that if instead of 101 teams, if I had 1,000 teams or 10,000 teams, then the relative frequencies would have very closely matched the theoretical probabilities over here. Okay, so this is an example of a binomial distribution. What defines a binomial distribution? All right, what is a binomial experiment? First of all, okay, so basically the Monty Hall game that we played and this game we're going to talk about here, they're going to represent binomial experiments, which give rise to binomial distributions. So let's say that I'm playing Yahtzee and I roll a standard 6-sided die 5 times, or equivalently, I roll 5 such dice at the same time. Let's say that we count the number of 4s on the 6 dice. Let X be the number of rolls or the number of dice coming up of 4 among the 6 faces. Now this is a binomial experiment,
5 faces.
and X, which counts the number of 4s, is a binomial random variable. Now why is this a binomial experiment? Okay, so first of all, and don't worry, you won't be tested on this, but you need to know a binomial experiment when you see it. First of all, we see a fixed number of independent trials. In this case, for the dice, 5 rolls or 5 dice. For Monty Hall, it was 18 rounds for each of the student teams. Each trial results in either a success or a failure. So with the Monty Hall rounds, the contestant either won the car or didn't. For the dice, a success is when a 4 is rolled. A failure is when something else is rolled, like a 5 or a 6, or a 1, 2, or 3. So the idea is that we're counting successes. X is a binomial random variable that counts successes, which would be car wins in Monty Hall or 4s in this dice example over here. In some medical situations, X could count deaths, in which case you may not want to be successful. Number 3, for each trial, there is a fixed probability of success. And we call that fixed probability P. In the case of dice, P, the probability of rolling a 4, is 1/6. The failure probability is the complement. It's 1 minus P, or what we call Q, the failure probability. Q is 1 minus 1/6, or 5/6. It's the probability that a die comes up something other than a 4. In the Monty Hall problem, P is 2/3 and Q is 1/3. Okay, so in both the dice example here and the Monty Hall problem, we're talking about binomial random variables, X, which counts the number of successes from a binomial experiment. Another classic situation is when you're flipping coins. Here is another Rossmann chance applet. Let's say that we take a fair coin, probability of heads is 0.5, and we toss the coin, how about 100 times, like many of you did in the extra credit problem. Okay, let's draw the samples. All right, and this particular student got heads 44 times and tails 56 times. Okay, now let's say that instead of 1 student, we had 1,000 students flipping 100 coins. So 1,000 students doing this extra credit problem. Let's draw the samples. All right, this was the last student. We care really about this relative frequency histogram over here.
So the captions are in the way there. Look at that. Look at that. Kind of what shaped. Kind of what shaped there, by the way. We'll talk about that.
You can see that it's peaking at about 50 heads out of 100. Now, this is what we're seeing from the simulation where 1,000 students are flipping a coin 100 times, a fair coin 100 times. According to the binomial distribution, the frequency distribution should look something like this in green. And as you can see, it very closely models what we actually saw from our simulation.
Okay, so without the captions, you can see they match up pretty well. And you can see that it is roughly bell-shaped. The model is about bell-shaped.
And guess what? this binomial histogram very much resembles a normal bell curve. And in fact, we're going to investigate that later on. The fact that normal bell curves can sometimes approximate binomial histograms. Okay, so we're going to talk more about binomial experiments and binomial distributions in our next video.
Oh, hand up. I'm not used to hand up, by the way. Is there a question? Oh, good. You can put in chat or you can speak. Any questions?
Oh, I was gonna back to that video
Right.
about the doors opening.
The Monty Hall, right.
Yeah. Why would you want to open the door that's remaining? I thought the whole point was that the host didn't want you to get the money.
Right. So the idea is that you pick a door and like number one, you pick door number one, right? In fact, I'll do it. You pick door number one, right? And let's, okay, so I picked door number one. All right. Now here's the thing. Then I can either switch to door number two. Oh, I can either stay on door number one or switch to number two. Now the host will never show you the money, right? So the host is showing me door number three, and there's well, he's not going to show me the money, right? I mean, there's no way he's going to open the door and say, oh, hey, here's the money, because I'll just run after the money, right? So here, he can only show a door with the goat, and then he gives me a choice. Well, do I want to stay on my current door or switch to the other unopened door? So the thing is, I can only choose among the unopened doors. The host will never show you the money, right? So is that answering your question, or?
Yeah.
Okay. Are there any other questions? Okay. Yeah, if you have a question, it might be better to do chat. I mean, hands up. I'm not usually used to seeing the hand up, but all right. Okay, so oh, and by the way, if you want to have a little bit of fun, and you can all do this right now. Here's the coins applet. You know what I just did. Go ahead and do the coin applet over here. Click on that. All right. And so if you go to, see, probably the heads is 0.5, number of tosses. How about 100 tosses? Like every student flips the coin 100 times. Number of repetitions. How about 1,000 students? Draw samples. All right. So why don't you all do that and see if you all get a bell curve? You should all get roughly a bell curve. Okay. Again, this is what the last student got. We don't care so much about that. We're looking more at this, this distribution, right? So we had a bunch of students getting like between 46 and 54, right? Trails off. You're all pretty much getting something like this, right? A rough bell curve. Okay, I'll give you a moment. I'll give you 30 seconds. Okay, so you all got that kind of rough bell shape, right? And again, for these situations, a normal bell should be able to approximate it. We'll talk about that later. All right. So again, feel free to save the chat. You can go to the three dots to save the chat, and you can go back to this link. Okay, I do have to email some links later on. All right, now let's go back to the videos here.
Hi, everyone. We're continuing with Lesson 18 on binomial distributions. So far, we've talked about 3 binomial experiments that give rise to 3 different binomial distributions. These are distributions for x, a binomial random variable, which counts successes. So in the Monty Hall problem, we had students in teams play 18 rounds of the Monty Hall game. X counted the number of successes among those 18 rounds. And it turned out that X had a binomial distribution where N, the number of trials or rounds, was 18, and P, the success probability per round, was, perhaps surprisingly, 2/3, not 1/2. And we saw that this distribution in tabular form looked like this. X, the number of wins, went from 0 to 18, and here are the corresponding probabilities with a peak at 12. Now, this is a binomial distribution because we have a fixed number of independent trials, n equals 18, and what happens in one round does not impact another round. Each trial results in a success or a failure. A success means, of course, you win the car. A failure means you win the goat. And the success probability is fixed. It's 2/3, and it does not change from trial to trial, from round to round. Now, I also mentioned a coin experiment. Let's look at the Rossmann chance applet. Let's say we have a fair coin where the probability of heads is 0.5. And let's say that a success is heads, not tails. Although remember, something like a death could be a success. Here, a success is heads. Let's say that the coin is flipped 100 times. Okay, so this student gets 54 heads and 46 tails. You see the little dot there on the 54. It's a dot plot. You see the dot there for 54. Okay, now let's say that we repeat this 1,000 more times. 1,000 more students flip the coin 100 times. So for the 1,001 students, this is the frequency histogram for the number of heads. The binomial histogram, where n equals 100, I'll bring this up here, where n equals 100, and p equals 1/2 or 0.5. The binomial distribution where n is 100 and p is 1/2 or 0.5. The histogram is in green over here, and it closely matches what we see from the frequency histogram. Okay, so again, in this coin experiment, we're seeing a binomial distribution for x, the number of heads. And this is, in green, a frequency distribution for x. Okay, so why do we have a binomial experiment in the coin situation? Because again, we have a fixed number of independent trials, n equals 100. Each trial results in a success or a failure. A success means a head, a failure means a tail. And for each trial, there is a fixed probability of success. For a fair coin, p equals 1/2, and that does not change. The coin is not made of bread. P stays at 1/2. It's made of solid metal. Okay, p is 1/2, q is 1/2. So in the coin situation, if x is the number of heads, the number of successes, then x has, as its distribution, a binomial distribution where n, the number of trials, is 100, and p, the success probability per trial, is 1/2 or 0.5, the probability of heads. Now, in the dice situation, this is where we're rolling a die 5 times, or we're rolling 5 dice, and x is counting the number of 4s that we get. Well, n equals 5 is the number of dice that we roll. A success means you get a 4, a failure means you don't. We have a fixed probability of success. It's 1/6. That's the probability of getting a 4. The probability of not getting a 4 is 5/6. So in our dice example, if x is the number of successes, the number of 4s among the 5 trials or dice, then x has a binomial probability distribution. X is binomially distributed where n is 5 and p is 1/6. N and p are the parameters for this distribution. If you change one of them, you change the distribution. If you change the number of dice, if you change the probability of a 4, then that changes the distribution. It turns out that the distribution table for this binomial distribution is this. Of course, we can get between 0 and 5 4s among the 5 dice. The probability of getting no 4s is about 40%. Coincidentally, the probability of getting 1 4 among the 5 dice is the same, about 40%. The probability of getting all 4s on the 5 dice is almost 0. It's not quite 0, so we put 0 plus, because it's very powerful to say that something's impossible. It's not impossible to get 5 4s on the 5 dice, but it's pretty close to 0. It's 0 to 3 decimal places. In fact, the probability of getting 5 4s on the 5 dice is about 0.000129. It's very close to 0. Okay, now, again, this is a dice scenario where we're counting the number of 4s among 5 dice, or among 5 die rolls. But there are other binomial experiments that give rise to this distribution. Going up the notes here, similar examples. Let's say that 1/6 of all Americans have cooties, this disease. We randomly sample 5 Americans. Now, I know that technically we have dependence here, but by the sampling rule, we can assume independence. The probability we get the same person twice by chance is minute. Let X be the number of Americans in the sample with cooties. So we have a binomial experiment here because we have independence. We have 5 trials, the 5 Americans. Each trial ends up in a success or a failure. Here, a success means you have cooties, so you may not want to be successful. And the success probability, 1/6, is the same for all 5 Americans. Again, we're assuming independence under the sampling rule. Let X be the number of Americans in the sample with cooties, and lo and behold, it's the same distribution. It's a binomial distribution where N, the number of trials, is 5, and the success probability, the probability that a given person, American, has cooties, is 1/6. And the binomial distribution looks like this. There's about a 40% chance that nobody among the 5 Americans has cooties, about a 40% chance that 1 American among the 5 has cooties, and so on. Another experiment that gives rise to the same distribution, a multiple choice test has 5 questions, so N equals 5. Each with options A through F. That's 6 possible options. A student guesses randomly on all 5 questions. So the success probability per question is 1/6. On any given question, there are 6 possible options, A through F. The student guesses randomly. There's a 1 in 6 chance that the student gets the question correct. Let X be the number of correct answers or responses. So on a test with 5 questions, X could be between 0 and 5. Okay, X counts the number of successes. And again, it has the same binomial distribution we've discussed. N equals 5 trials or questions. P equals 1/6, the shared probability of success.
Here, let me just show that again, right? Same distribution for all these examples.
In this case, the student guesses randomly. On any given question, 6 options, P is 1/6. So in all 3 of these cases, actually, now it's 5 examples where we have a binomial experiment. I just described 3 experiments where we have the same binomial distribution. We roll 5 dice and we count the number of 4s. X, the number of 4s we get, has a binomial distribution, N equals 5, P equals 1/6. In the cooties example, N equals 5 Americans, that's the number of people in our sample, the sample size. 1/6, that's the probability that any given American has cooties. On this multiple choice test, N equals 5 questions, P equals 1/6, because each question has 6 options and the student guesses randomly. So for this student, the probability the student gets no questions correct, all wrong, is about 40%. The probability the student gets exactly 1 question correct turns out to be the same, about 40%. And there's almost no chance that the student gets all 5 questions correct. It's this over here. Okay, so we'll continue with this in the next lesson.
Right. Any questions thus far? That's the probability distribution table that applies to all these examples with binomial, N equals 5, P equals 1/6. For dice, for cooties, the medical example, for testing, they all correspond to this table. Okay, so many different applications for this table. All right. And by the way, in case you're curious, before I forget, I'll show you this later on, but here's a gallery of binomial histograms where N equals 1, 2, 3. So for example, for a fair coin, right? Let's say a success is getting a head, all right? P equals 1/2. If you flip the coin once, probability is 1/2 you get no heads. Probability is 1/2 you get 1 head. If you flip the coin twice, it's more likely that you get 1 head out of the 2 flips, but you could get no heads or 2 heads, right? So the height corresponds to probabilities. These are binomial histograms, and we'll talk about these, all right, for various values of P and for N.
Hi everyone, we're continuing with lesson 18 on binomial distributions. And last time we really focused on this one particular distribution, this binomial distribution where n equals 5 trials and success probability p equals 1/6. This is the distribution in tabular form. And we saw applications of this to rolling dice and counting the number of 4s, to the cooties example, where we took 5 random Americans and counted the number of cooties cases, and the multiple choice test with 5 questions, each A through F. The student guesses randomly, and we count the number of questions the student gets correct. Actually, we can modify the coin situation for this distribution. Now, in the usual situation, we have students flip a fair coin 100 times. A head is a success, and X counts the number of heads or successes. Then X has a binomial distribution where n equals 100 flips or tosses, and success probability, head probability, P, is 1/2 or 0.5. So let's say that P is 0.5, the probability of heads. We have n equals 100 flips or tosses. This student gets 51 heads and 49 tails. We see a dot at 51 on the dot plot.
Okay, so here's the dot plot. I know the captions cover up stuff. By the way, these are some of my earliest videos, because remember, we went online March of last year. So this is one of my early videos. See that dot there, right?
Let's say that 1,000 more students join in the fun, do the same thing. Student number 1001 gets 52 heads over here. And here is a frequency histogram for the number of heads, the value of X, obtained by the 1001 students. Now, what would the corresponding binomial probability distribution predict in terms of the frequency histogram? It predicts what's...
So that's in green, and it's pretty close, right?
In green, which is a pretty close model for what we actually see in our simulation. Now, this green histogram is given to us by this distribution, a binomial distribution where n equals 100 and p equals 0.5. That's the ideal theoretical distribution in green. Now, what happens if we consider this alternate distribution where n equals 5? We're just rolling 5 dice or flipping 5 coins here. But this time, the probability of success P is 1/6. So we're modeling rolling 5 dice where we're counting the number of 4s, or we're flipping a very unfair and biased coin where the probability of heads is 1/6, not 1/2. So let's say the probability of heads is about 1/6, about 0.167. That's the decimal equivalent rounded off. Okay. 5 flips or 5 rolls of a die. One sample. Let's see what happens with one student. Now here it looks a bit different. So basically, it's like a student rolling the die 5 times, or rolling 5 dice, or flipping a biased coin 5 times. So each of these wheels here corresponds to a die roll or coin flip. Now, 1/6 is the proportion of each disc that's blue. That corresponds to a success. So if this spinner lands in the blue wedge, that counts as a success. For example, here, this barely counts as a success. The spinner barely enters that blue wedge, that counts as a success, which means that the die came up a 4 or the biased coin came up heads. But in these 4 other rolls or flips, the spinner landed in the pink area, which corresponds to a failure, or 5/6 of the pie. So we had 4 failures over here because the spinner landed in the pink failure pieces of the pie. So among these 5 die rolls or coin flips, we had 1 success, just barely, and 4 failures, 1 head and 4 tails, if 1/6 is the probability of heads. Now, what happens if we do this let's turn off the binomial. Let's say that we do this 1,000 more times. Notice that the dot here indicates we had one success for this one student rolling 5 dice. If we have 1,000 more students, here was the result for student number 1001. Again, one success.
So here's what it looks like. All right, that's what it looks like.
Okay, so it looks like we have a bunch of students who got either no 4s or 1 4, fewer students with 2 4s, even fewer students with 3 4s, or in the context.
Right. So here's a number of students with 0 4s, 1 4, 2 4s, 3 4s. Basically, no one got 4 or 5 4s.
Of coins. Remember, it's a very biased coin where the probability of heads is 1/6. We had many students who got no heads, many students who got exactly 1 head, fewer students who got 2 heads out of the 5 flips, fewer. Okay. By the way, what does the binomial distribution over here predict? The binomial distribution predicts this frequency histogram over here.
So you see it's pretty close, right? The green bars, that's for the exact binomial prediction, okay, like for relative frequencies. And the black bars represent frequencies. So we're kind of mixing relative frequencies and frequencies. So the green bars, the heights correspond to the frequencies predicted by the probabilities in the exact binomial distribution. So they're the projections.
Here in green. So again, the binomial histogram, or really the frequency histogram predicted by the binomial distribution, does a very good job of the actual frequency distribution we see for the 1,001 students. Okay, so here again, we're looking at a twisted or biased coin situation where we end up with the same binomial distribution as this guy over here. And what we see is what we get. I mean, in terms of the actual simulation, we get a frequency histogram that's very close to what the exact binomial distribution predicts for us. All right. So now, back to these notes. Now, fortunately, the notes that are primarily handwritten, these will not be on the homework or the exam. This describes how the probabilities are computed. I'll discuss these in later optional videos. Now, what's still required? Well, first of all, we have the sampling rule. Remember, when we had the cooties example, we were drawing a random sample of 5 random American adults, I guess, from the overall population. And by the sampling rule, we could still assume independence. We could still have a binomial experiment because the sample size, little n, was tiny. It was only 5. And it was certainly no more than 5% of the overall population size of American adults, which is in the millions. Okay, so we could assume independence. That's a side note. What else would be fair game for homework or potential exams? Well, let's say that we have this example here. Example 2, using tables to analyze binomial distributions. Let's say that 70% of American adults like Senator Smith. That is, the probability that a random American adult like Senator Smith is 0.7. Bear in mind, there's often a direct relationship between proportions and probabilities. 70% of American adults like Senator Smith, that's a proportion. That's readily translated as a probability. The probability that a random American adult like Senator Smith is 70% or 0.7. There's often a relationship between proportions and probabilities. Now let's say that 6 American adults are randomly sampled to form a focus group, and we want to ask them questions about Senator Smith, their opinions of Senator Smith. Find the probability that at least 4 of the people in this focus group of 6 like Senator Smith. Big hint, we have this table here. Now, on an exam, it's fair game for you to be required to know that the distribution we're talking about is this distribution. If we let X be the number of people in the focus group who like Senator Smith, then X has this as the distribution. A binomial distribution where n equals 6, that's the number of trials, the sample size, the number of people in the focus group, and p equals 0.7, the success probability per American adult. Now, we're saying here that a success means that an American adult likes Senator Smith, and we're counting successes. So X, the number of successes, can be an integer between 0 and 6. And it turns out that these are the corresponding binomial probabilities. Now, on an exam or a homework problem, I would give you this table of probabilities. Later on, in optional sections of videos, I will discuss how these probabilities are actually obtained. But for homework and or exams, I would actually give you this probability table, this probability distribution table. It's a table for this distribution. Okay, so the probability that nobody in the group likes Smith is almost 0. Bear in mind, Senator Smith is pretty popular, and the probability that nobody among the 6 people in the group likes Smith is almost nothing. Now, 70% of American adults like Smith. It's not surprising that the most likely number of people in the group who like Smith is 4. 4 out of 6 is pretty close to 70%. 2/3 is pretty close to 70%. The probability that exactly 4 people like Smith is 0.324. After that, the probabilities go down. The probability that all 6 people like Smith, it's lower, 0.118, but not terribly low. Senator Smith is very popular, and the probability that all 6 like Smith, it's not too low. It's lower than the probability of 4 liking Smith, but it's not that close to 0 either. Okay, so
I need to note, in today's politics, almost no one in America has a 70% approval rating in politics. Maybe Tom Hanks, I don't know.
given this probability distribution table, my question here was, find the probability that at least 4 people in the focus group like Senator Smith. So this is similar to what we've done before. What's the probability that X is at least 4? Basically, we're focusing on these 3 rows of the table, and we want to add these probabilities. Remember, at least 4 includes 4, so we want to include this probability, and we also want to go higher. We also want P of 5 and P of 6. In the end, we want to add P of 4, the probability of exactly 4 people liking Smith, P of 5, the probability of exactly 5 people liking Smith, and P of 6, the probability that all 6 people like Smith. We're going to add these probabilities. Again, these probabilities are fairly high because Senator Smith is popular. The probability that X is at least 4 is P of 4 plus P of 5 plus P of 6. We add up these 3 probabilities, we get 0.745. So about a 3 in 4 chance that at least 4 people in the group of 6 like Senator Smith. And that would be fair for a homework or exam question. So afterwards, we're going to deal with basically optional videos where I'll discuss how these probabilities are computed. But we're going to talk game shows and we're going to have fun as well. I'll see you later.
Okay, so I'll admit this. If you're just concerned about finishing the homework, then you have enough at this point. But as I said, if you're curious about how these probabilities are generated, and hey, I'm going to show you some game shows because I'll show you how binomial probabilities and distributions come up in game shows. All right. So if you just want to do the homework, that's enough. But I encourage you to stick around. All right. Let's see what's up.
Hi, everyone. We're continuing with lesson 18 on binomial distributions. This was the problem that we did last time. Later on in part F, these are handwritten notes, and these are notes that we'll cover much later on. They're optional for now. So I'm going to...
Oh, before I get to that even, I want to go back to my gallery here. Remember the Senator Smith problem, right? So n equals 6, that's the number of people in the focus group. P is 0.7, which is kind of close to 3/4. 3/4 is 0.75, right? So take a look at this distribution. There's probably a histogram here, right? So this histogram does a pretty good job of emulating what I showed you in the previous video, right? So, about 12% that all 6 people like Smith. And then it was most likely that 4 or 5 people like Smith, right? Almost no probability, 0 probability almost, that no one likes Smith. So this approximates the probability histogram for the Smith problem. N equals 6, P equals 0.7, or really 0.75 here, all right? And then here's the corresponding probability histogram, an estimate. Anyway.
to go over the handwritten optional note backwards. So again, part F, we're not going to deal with right now. Part C, you won't have to know for the exam, but it's one of the most beautiful things in math. So let's go to more beautiful websites. Pascal's triangle, which is really optional. And folks, believe it or not, this here is Pascal's triangle. One of the favorite games on The Price is Right.
Right. So I have a better, just for better clarity here. All right, so there we go. You see, it's a lot worse here.
36 years of Price is Right, $30,000. We'll be right back with more Price is Right right after this.
So that is the Pascal's triangle. Plinko is Pascal's triangle. Let's go to this great website, mathisfun.com, which does a great job with Pascal's triangle. So how is Pascal's triangle constructed? You might remember this from your algebra class. So you start off with a tent of ones. So you have ones along this edge and ones along this edge, like a pyramid. Now, every time you have two consecutive numbers, they give birth to their son, their sum. So for example, here, the 1 and the 3 give birth to a 4. So up here, 1 and 1 give 2. Over here, 1 and 2 give 3. 2 and 1 give 3. And then here, 1 and 3 give 4, as they show. 3 and 3 give 6. 3 and 1 give 4. By the way, one of the properties of Pascal's triangle is that it is symmetric. If you draw an axis here, you see the left and the right mirror each other. The left half and the right half mirror each other. And Pascal's triangle is gorgeous. There are so many patterns. Of course, you have ones along this diagonal. You have the positive integers on this diagonal, the triangular numbers. Imagine dots like 1, 2, 3, right? On this diagonal. Again, we have symmetry, left side and right side. If you add up the sums, and we'll see why this is true, 1, 2, 4, 8, 16, and so forth, powers of 2. And there are reasons for that. Surprisingly, exponents of 11 are hidden in here, powers of 11. The Fibonacci sequence, remember, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5. Each successive Fibonacci number is the sum of the two prior Fibonacci numbers. It's a famous sequence, and it's also hiding in Pascal's triangle. If you shade in all the odd entries, and you do it for many rows, you get the Sierpinski triangle or gasket. It's this thing, which is a famous creature in chaos and fractal theory. The idea that basic rules lead to these elaborate, complex patterns. Okay, now we saw the powers of 2 before, and this kind of explains why. For example, consider 3 flips or tosses of a coin, fair or not, right? Well, how many possible sequences of 3 heads or tails can we have? Well, we have 3 flips or 3 positions. Each position can be a head or a tail, right? So we have 2 possibilities for the first flip, 2 possibilities for the second, and 2 possibilities for the third. 2 times 2 times 2 is 8. Now, Pascal's triangle, let's look at this. 3 flips or tosses of a coin, fair or not, all right? Notice there's only one way to get 0 tails and 3 heads, 3 ways to get 1 tail and 2 heads, 3 ways to get 2 tails and 1 head, and only 1 way to get all 3 tails. These are the numbers in Pascal's triangle on row number 3. Bear in mind, when you look at Pascal's triangle, row number 0 is on top. So row number 0 has the 1. Here's row number 1, row number 2, row number 3, and so forth. You can look at the second number in the row to see what row number we're talking about. Now, it turns out that Pascal's triangle is this list of binomial coefficients over here. N choose K, or NCR. Do you remember those numbers? Remember 52 choose 5? or 52C5, the number of possible poker hands from a deck of 52 cards. That's 52 choose 5. That's way down in the table in Pascal's triangle, but it's there. So basically, if you're like Vanna White on another game show, if you flip these binomial coefficients around, these NCR values, you're going to get Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so forth. Here are the first 15 lines of Pascal's triangle, rows 0 to 14, and the ancient Chinese knew about it. I want to go back to why it is that these binomial coefficients, these NCR numbers, the number of combinations of n items taken R at a time, like poker hands, why they correspond to Pascal's triangle. All right. Well, again, this is why it's Plinko. Let's go back to this Plinko board over here, this Pascal's triangle. All right. In fact, I'll go to the very top. All right. So how many ways are there to hit this pin over here? Imagine that each of these squares corresponds to a pin. How many ways are there to hit this pin over here? 3 choose 1 or 3. Left, left, right, left, right, left, and right, left, left. We're imagining these falling chips. How many ways are there to hit this pin over here? Only one way. Left, left, left. Well, there's one way to hit this pin and 3 ways to hit this pin. How many ways are there to hit this pin? 1 through here, and then go right, 3 through here, and then go left, 4 ways to hit this pin. So the number on each of these squares, these numbers in Pascal's triangle, they correspond to the number of ways that the chip can hit that pin. Let's go back here. Why is this 3 choose 1? 3 choose 1 is 3, all right? So 3 drops, n equals 3. A right is a success. Right is a success. So left, failure, right, success. That's one way to get 1 success and 2 failures. Left, failure, right, success, left, failure. Again, another way to get 1 success and 2 failures. 1 right, 1 success, 1 left, a failure, another left, a failure. So how many ways are there to get 1 success and 2 failures out of 3 trials or 3 drops? 3 ways, 3 choose 1. So that's an example of why Pascal's triangle is a table of these binomial coefficients, the number of combinations, NCR, n items taken R at a time. Again, 52 choose 5 is way down here, about 2.6 million. At the very bottom, again, the Plinko board. It's called a quincunx. So let's say that it's 50-50. P is 0.5 in a binomial distribution. Let's speed it up. Here, n equals 6, p equals 0.5. And we're looking at what a binomial distribution where n equals 6 and p equals 1/2, what that histogram would look like. And take a look at this. It's looking more and more bell-shaped. What if we up it to 15? N equals, let's restart this. N equals 15, p equals 0.5. Sped up, looking down there. N equals 15, p equals 0.5. Binomial distribution. Again, a right is a success, a left is a failure. Each drop is a trial, which means that these numbers here correspond to the number of successes. If you're a student who gets all 15 questions correct on a true-false exam, for example, then you'd be in this bin over here. Not very likely, though. And again, it looks more and more bell-shaped. All right. And they explain the quincunx over here. Again, it's a great website. Great website. Okay, and a normal distribution approximates that. But Pascal's triangle is absolutely gorgeous and is relevant to the binomial distribution, as we'll see in the next video.
Okay, any questions? Again, this is the fun stuff, and it shows you why these things work. Okay, because it's curious, right? Because these are very important distributions.
Live TV from 85 plus channels with local sports and news. YouTube TV. Try it free.
Hey everyone, we're finishing up lesson 18 on binomial distributions, but we took a detour towards Pascal's triangle, which is one of the most beautiful things in math. I talked mostly about it last time, but I wanted to add in a few finishing touches here. This is a handout I created about the magic of Pascal's triangle. So as a quick reminder, remember we put ones along these edges of this tent or pyramid here, right? And every time we get two consecutive numbers, they give birth to their sum. Their sum is a sum. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, and so forth. And I claimed that these numbers in Pascal's triangle were in fact these binomial coefficients, these numbers of combinations, n choose r. So for example, 3 choose 1 is 3. And that corresponds to the number of ways for a Plinko chip to hit the 3. There are 3 drops, n equals 3, drop, drop, drop. Okay, a right is a success, a left is a failure. So how many ways can you get 1 success out of 3 trials? 1 right out of 3 drops? Well, left, left, right, left, right, left, and right, left, left. 3 choose 1 is 3. Now, how is this related to the binomial theorem from algebra? So you might remember from algebra class that a plus b all to the third can be written like this, right? Where for the variable parts, we start with a to the third, we decrease the exponent by 1 until the a disappears. And then for b starts off as b to the 0, which is 1, which is invisible. And then we get b to the second, b to the third. And the coefficients for this power of a binomial, right? These coefficients come from Pascal's triangle. It's these binomial coefficients, these n choose x guys. N choose 0, n choose 1, n choose 2, n choose 3. 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, 3 choose 3 is 1. Now, why does that make sense? How do we get the cube of a plus b? Well, if you cube anything, you take 3 copies of that thing, here a plus b, and you multiply them together, and you can distribute like crazy. But basically, when you perform the distribution, for each term, you get a choice from here, a choice from here, and a choice from here. It's kind of like if you have 3 meals in a day: breakfast, lunch, and dinner. For breakfast, you can pick super salad, A or B. For lunch, A or B, super salad. For dinner, A or B, super salad. Okay, now again, instead of salad, we can talk about B, or a success, or getting a question right, or getting ahead, okay? So basically, if you choose a term from here, and then choose a term from here, and then choose a term from here, there are 8 ways to do that. 2 times 2 times 2. 2 to the third is 8. So you could have all soup, right? A. That could be all failures. The number of ways to get 0 successes out of 3 trials. The number of ways to get 0 questions correct on a 3-question exam, 1 way. Wrong, wrong, wrong. A is wrong, B is right. But how many ways can you get 1 question right and 2 questions wrong? How many ways can you get 1 success out of 3 trials? Well, you could have wrong, wrong, right, wrong, and right, wrong, wrong. When you add these together, you get 3 A squared B. The 3 here is the number of ways to get 1 question right out of 3 questions. Likewise, 3 choose 2 is also 3. That's from symmetry. The number of ways to get 1 question right out of 3 is equal to the number of ways of getting 1 question wrong out of 3, or 2 questions right out of 3. So there are 3 ways to do that. You add these up, and you get 3ab squared. These 3 guys here. And then there's only 1 way to get all 3 questions correct on a 3-question exam. Correct, correct, correct. That's b cubed. Add these all together, and you get the expansion of the cube of a plus b. So if you love algebra, I'm sure you love that. Okay, So how do we use these ideas to figure out binomial probabilities? It's all related. The binomial theorem, right? These binomial coefficients and binomial distributions with their binomial probabilities. So for example, if you have a student taking a multiple choice test with 5 questions, n equals 5 trials or questions, and each question is A through F, 6 options, and the student guesses randomly on each question. The student knows nothing about the material and guesses randomly. So the probability of getting any given question correct is 1 out of 6. Let X be the number of successes, the number of questions the student answers correctly from guessing randomly on this test. The possible values are 0 through 5. The student could get all the questions wrong, 1 question correct, 2 correct, 3 correct, 4 correct, or all 5 correct. And here are the corresponding probabilities. But how can we figure out these probabilities? Again, this is optional for the homework and the exam, but it's good to see. All right, well, you could have software or TI graphing calculators. You could have printed tables, or the old school way of doing it, the binomial probability formula. The probability of X successes equals N choose X, or NCX. That's a binomial coefficient. Like 52 choose 5 was the number of 5-card hands you can get from a deck of 52 cards. N choose X, or NCX, is the number of ways that a student can get X questions correct out of N questions. So for example, okay, so for,
Yeah, I think I may have made a mistake, so I had to kind of cut in there. All right.
for example, how can a student get, let's see, 3 questions correct out of 5? 3 questions correct out of 5. 3 questions correct out of 5. It turns out there are 10 ways. 5C3, or 5 choose 3, is equal to 10. For example, the student could get question 1 correct, question 2 correct, and question 3 correct. The student could get question 1 correct, question 2 correct, and question 4 correct. The student could get the last 3 questions correct, number 3, number 4, and number 5. It turns out there are 5 choose 3, or 10 ways of doing this. All right, so N choose X is the number of ways that a student can get X questions right out of N questions. P is the success probability per question. X is the number of successes. Q is the failure probability per question. And minus X is the number of failures. So for example, if there are 5 questions, if N equals 5 questions, X equals 3 correct, then N minus X equals 2 wrong or incorrect. Okay, so you can make these computations. Probability of 0 correct. That's the probability of getting all 5 wrong. It makes sense that it's 5/6 to the 5th. The probability of getting each question wrong is 5/6. Multiply 5 copies of this by independence, and you get about 40%, 0.402. Remember, on your calculator, make sure you process 5 divided by 6 first before raising to the 5th power. P of 1, 5 ways to get 1 question correct out of 5, and only 1 question correct, right? Again, about 40%. That's a coincidence. The probability of 2 questions correct, that's about 16%. The probability of 3 questions correct, the probability of 3 questions correct. Let's go through this in detail. 5 choose 3, 5C3. We just mentioned that that binomial coefficient was 10. There are 10 ways of getting 3 questions correct and 2 questions wrong on a test of 5 questions. That's 10. All right, the probability of getting each question correct is 1/6 because it was A through F for each question. 6 possible options. The student is guessing randomly. 3 questions correct, 1/6 to the 3rd. The probability of failure, the probability of getting a question wrong, Q, is 5/6, which is 1 minus a 6th. 5/6 to the number of failures or questions wrong, that's 2. Right? You put these all together, 0.032, or about a 3% chance that the student gets exactly 3 questions correct out of 5 based on random guessing. P of 4 is smaller. P of 5 is very, very tiny because you have, for example, 1/6 to the 5th over here, which is teeny tiny. 5/6 to the 0 is 1. 5 choose 5 is 1. So it's basically 1/6 to the 5th. The probability of getting 5 questions correct, success probability of 1/6 for each question, 1/6 times 1/6 times 1/6 times 1/6 times 1/6, it's almost 0. It's this. So that's how you calculate the probabilities. Okay. So when all is said and done, you end up with this binomial formula. Applying it, you get this. For this distribution, here is the probability table. The binomial probability distribution for this distribution as a table. Now, why does this make sense? Why does this make sense? Okay, so let's take a look at one way to get 3 questions correct out of 5. Well, one way to get 3 questions correct out of 5 is you get the first correct, the second correct, and the third correct. Whereas number 4 and number 5 are wrong. So what's the probability of getting number 1 correct by random guessing? 1 out of 6, which is the value of P. The probability of getting number 2 correct, 1/6. The probability of getting number 3 correct, 1/6. Now the probability of getting number 4 wrong is 5/6, which is Q. And the probability of getting number 5 wrong is 5/6, which is Q. So that's one way to get 3 questions correct out of 5.
So again, these probabilities multiply together. Okay. Correct, 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 wrong, wrong.
If you get the first 3 correct and the last 2 wrong. The thing is, though, there are more ways of getting 3 questions correct out of 5 questions. In fact, there are 10 ways, 5 choose 3 or 10 ways, which means that this is the probability of getting question 1 correct, question 2 correct, question 3 correct, and question 4 wrong, and question 5 wrong. This is only one way of getting 3 questions correct out of 5. And this is the probability of that one particular way. But there are 10 ways to get 3 questions correct out of 5. So this has to be multiplied by the 10. Hence, P of 3 looks like this. 10 ways to get 3 questions correct out of 5. 1/6 to the third, 5/6 to the second. Because we may as well look at this easy case where the 3 questions you get correct are the first 3. But it's the same probability for all 10 ways of getting.
So 10 times this. Here's the probability of getting correct, 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 wrong, wrong. All right. 1/6 to the third times 5/6 to the second. Okay. There are 10 ways to get 3 questions right and 2 questions wrong. For example, you could have correct, correct, wrong, correct, wrong. Right. 10 times this. Because there are 10 ways of getting 3 right and 2 wrong. Here's one way of getting 3 right and 2 wrong. Here's a probability, but it's the same probability for all 10 ways.
3 questions correct out of 5. Again, that's how you get the table. You don't have to know that for homework or exams. And that, my friends, is the binomial distribution.
And in the last video, I have comments about why it's called binomial.
Hello again. I wanted to explain why these binomial distributions are called binomial distributions and also show you some lovely pictures. So remember, for a binomial experiment, each trial results in a success or a failure. Each trial is binary, success or failure. Just as a bicycle has 2 wheels, a binomial experiment has a binary result for each trial. Each trial results in either a success or a failure. The coin comes up heads, success, or tails, failure. A student gets a question correct, success, or wrong, failure. The die comes up a 4, success, or doesn't, failure. Also, another reason why it's called a binomial distribution, because as I mentioned earlier, it's involved with expanding the powers of binomial expressions. A plus B is a binomial, a two-term polynomial. The cube of A plus B, it can be worked out in this fashion, and these coefficients are called binomial coefficients, the 1, 3, 3, 1. They're called binomial coefficients. Also, these pictures, a gallery of binomial histograms. I have 50 of them here for various values of n, the number of trials, like for example, the number of questions on a test or the number of coin flips, and p, the success probability per trial. For a fair coin, you're looking at the center column. For p equals 1/4, that could be a multiple choice test, A, B, C, D for each. But anyway, look over here, for example. You flip a fair coin 3 times. N equals 3 trials, P equals 1/2. The probability of no successes, no heads, is 1/8. The probability of 1 head is 3/8. The probability of 2 heads is 3/8. The probability of all 3 flips being heads is 1/8. Notice this is symmetric. A related problem, if a student takes a multiple choice test with just 3 questions, maybe it's a short quiz, 3 questions, each of them true, false. The student guesses randomly on all 3 questions. Then again, here's the probability distribution for X, where X is the number of questions correct on the student's part. Now let's examine these binomial histograms and notice, especially in that center column, as n gets larger and larger, n equals 10, p equals 1/2. This is the simplest binomial histogram that we're going to approximate with a normal bell curve. Something to look forward to.
All right, so that's that. All right. And that is those are the lessons for the homework, lessons 11 through 18. All right, lessons 11 through 18. Lesson 18, that was very deep, right, on binomial distributions. Okay, we're going to discuss the homework on Wednesday, so give me your best shots on Wednesday. In fact, many of you might feel comfortable turning in your homework after Wednesday. So give me your best shots on Wednesday, and then we'll cover the homework quickly but more comprehensively, perhaps, the following Monday, the 22nd. Homework's due Tuesday, the 23rd. Again, after finishing the most recent batch of homework, I can finally get your homework 1 batch, okay? And I'm hoping that there aren't too many problems in my department. I'm the assistant chair, so I gotta deal with that stuff. So that's why I can't make predictions, because I don't know what's going on in my department. I'll find out. Okay, anyway, so we're going to discuss homework the next 2 sessions, all right? And then we'll start the third part of the class right before spring break. All right, so thank you for hanging in there. Are there any questions right now? Any questions right now?
Yes. I just have some very specific homework questions. I'm not sure if this is the right time.
That's fine. Right.
Okay.
Okay. Now, first off, are there any people with any like general administrative questions, like any short, quick administrative questions? Otherwise, I can go ahead and address particular questions. Let me grab a whiteboard here. Let's see here. Okay. Let's see. Okay, I'll grab the homework also. You're talking about problems on the homework, correct?
Correct.
Correct. Okay, homework 2. Okay, which lesson?
Lesson 11
11?
and 12.
11 and 12, okay. Okay, which questions?
I'm looking first at question 4 of lesson 11. And then, let me see. Question 3 of lesson 12.
Okay, so let's start with a couple here. So,
I should say in particular, actually, I'm interested in questions 4 and 5 of lesson 12.
12, so on 12, 3, 4, and 5?
Yes.
Okay.
I'm not sure if it would be easier for you to see what I already did, because I already went through all these problems, and I think I have some valid answers, but I wanted to understand them a little bit better.
Okay, so it's up to you. I can either work them out on the whiteboard, or if you're welcome to do a share screen if you wish, or a share video or share screen. But it's up to you. You can share video, share screen, or we can just work it out here.
Okay, let me see. I'm thinking, first of all, I think the questions on lesson 11 should actually be very quick and easy. So I was wondering, would it be okay for me to just write the dice combinations in parentheses instead of drawing the table
The grid.
for
Yeah.
each?
Yeah. So basically, in your showing of work, you should either do the grid or give me the list of ordered pairs, or maybe you can actually give me a stated rationale, even, right? But you should do some justification.
Sure. Okay. May I?
Go ahead. No, so like on lesson 11, number 4, there are many of these, A through H. Is there a particular one you want to hone in on?
Oh, let me take a
Or like
look
a sample,
here.
like a sample,
Sure. Let me see. Okay, I think it might be. Let's see. Sorry.
It's okay.
Maybe actually number 5 has a similar setup. Here, I'll turn on my camera so you can see what I wrote already. Okay.
Okay, so can you take control? Let me see.
All right, can you see that?
Okay, so how? Let me see how this is gonna work. Maybe stop. Okay, so I'll put stop share here. Yeah. Okay.
Oh,
Okay.
okay.
Yeah. So stop share, and then let me grab you here. Oh, okay. So how am I gonna do this? If I want to focus on one student. Okay, so I'm trying to figure out how I'm going to. How does this work? Yeah. So how can I get one student view speaker?
Yeah, that should work.
Okay, view speaker. Okay, and then do you have your video on?
Yeah. Okay, now I do.
Okay, so okay, and then speaker. Yeah. Okay. Yeah, that works. That works. So view
Okay.
speaker. All right. So
Okay.
and we're looking at number 5 here. Yeah, it's a little fuzzy, but number 5. Okay, so P of A bar is 1 minus P of A. That's always right. Oh, you're looking at the roulette one, right?
Yes.
Yeah, yeah. Okay, so I'm just gonna okay. Okay, so we're looking at yours. Okay, so 11.5. Okay, so what's the probability you will lose? Right. Oh, I see. I see. So the probability you will win is 9/19, right?
Yes.
So the probability you'll lose is 10/19 because you can say that's 1 minus 9/19, right?
Mm-hmm.
Yeah, and you're right. And then the second way you can do it is that it's 9/19 9/19 plus 1/19, right? Yeah, you're right. You're right. So those are 2 ways you can do it.
Okay.
Right. By
Okay,
doing
and
the
then
complement and by adding up the probabilities of getting a green or a whatever, a green or a black number. Yeah.
yeah, exactly. And
You're right.
then
Huh?
okay, and then let's see. For number 4, let's see, hold on. Okay, that's letter H there.
Okay, 4H. Okay. What is
Yeah,
the probability?
I wrote out all of the ordered pairs. Does
Okay.
that look good to you?
And that'll be sufficient. Probably the number on the green die is one more than the number on the red die. So you have 1, 2, 2. Let me see here. 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. So 5 out of 36. That sounds right, and that matches with my answer. That sounds right.
Okay.
Right. And in my grid, it'd be like a diagonal in my grid. That's another way. I'm more visual, so I tend to work more with the grid. But if you're more numerical, that's fine. Just go ahead and write down your ordered pairs. Yeah.
Yeah, I'm
I
a little
wanted
more
people to
numerical.
show some rationale. I mean, show some work, right?
Okay, definitely.
Yeah.
But
these don't have to be deep.
yeah.
Yeah.
Okay, and then okay. I guess it would be worth it for me because I think the rest are fine. Those were similar, the ones in question 4.
Oh, and by the way, are you okay that we're still recording, or would you like me to trim it?
It doesn't really matter to me.
Yeah. Okay, that's cool.
Okay. I'd actually like to show you question 3, part C, and then let's see, question 3, part D, and then 4 and 5 of lesson 12. So I'm good with lesson 11 now. Okay. So this is more difficult for me. Usually I do work better numerically, but this time I decided to actually draw the table out. And I just wanted to see if my reasoning looks good here.
And again, which one are we looking at?
This is part C of question 3 in lesson 12.
Okay. Okay. 12C. Okay. 3C. Right.
Yeah.
Okay. And by the way, I'm doing okay. There's a student in chat who's suggesting that another thing we could do is if you can take a photo of your work and email it. That's not a possibility, but I'm okay with this right now. But a student suggested that. All right. Anyway, so 3C. Okay, 2 standard 6-sided dice are rolled. One is red, the other is green. Doubles. Okay, so 3C. What's the probability of getting a 2 or a 4 on the red die, or a 3 on the green die? Yeah, that pretty much requires a grid. Yeah. It's hard to do without the grid. Yeah. Okay, so getting a 2 or a 4 on the red die, or a 3 on the green die. Right. I like the way you're thinking about it. Right. And then you only single count the X's. Right.
Yeah. Mm-hmm.
Right. So the answer 11, 12, 13. Oh, wait, 6, 12, 13, 14, 15. It's 16 over 36, right?
Yes.
Right, 16 over 36. And you don't have to reduce, but it is 4/9. You don't have to reduce though. But 16 over 36 or 4/9. Right. Yeah, you're right. Your reasoning is good. Yeah.
Okay.
Yeah.
Okay,
And
cool.
I like your comment. Count once. So you're you're writing about as much work as you could, basically. Yeah.
Yeah.
So
Okay.
far so good. Yeah. Yeah.
Okay. And then let me see. Okay, so I was just kind of checking in with these particular problems because I was struggling with them a little more. But this one, I think questions, let's see, 3D, 4, and 5 of lesson 12, I got stuck with. So, okay, so,
On lesson 12. Okay. And which one are you focusing on? So 3D. Do you want to start with 3D?
yeah, 3D and then 4 and 5.
Right. Okay. So 12, 3D.
Oh,
That's
3D. Sorry,
okay.
3D starts down here actually.
Yeah, doubles or a 3 on green. Okay.
Yeah.
Doubles or a 3 on green. And again, I would recommend doing a grid for that. So do you have a grid on the next one?
Yeah.
Yeah, doubles or 3 on green. I agree with that. Yeah. So 6, 7, 8, 9, 10, 11 over 36.
11 over 36. Yes.
Right.
Okay.
I would agree. Yeah, right. Uh-huh. So that'd be good.
4 and 5, I think, I don't know what went wrong, but they're different. They came out I think 4 and 5 are supposed to be the same, right? The
Yeah,
answer.
yeah, right. 4 uses probabilities, 5 uses the table. Okay, so on 4, what's the probability that an adult Fredonian owns a cat or a dog? So that's going to be, see, you're right, 0.35. Oh, and by the way, it's not so bad, but technically it's good to use decimals when you're doing calculations, but your basic idea is correct. Your basic idea is correct, but you should be getting the right idea anyway.
Okay.
Okay, but 10% own both, right? Yeah. Oh yeah, that's right. That's right. So number 4 should be 0.55 in decimal, right? Right. And then number 5 should reflect that. And you're not getting the same for 5. So, okay, so 5.
What I did for 5
What's the
is I took
probability? What's the probability that a randomly selected adult owns a cat or a dog based on the table? Right. Okay, so
I took the number of cat owners and the number of dog owners, excluding the number of cat and dog owners who own both. And then I put the total number of pet owners in the table in the denominator.
right, and I see that it's going to be too low. I'm trying to follow your rationale here. So you took the 2,000 and the 2,500. Okay, I see. So so here's the deal. You do pick up the 1,000 once because you do want the Fredonians who have both a cat and a dog, but you only count those 1,000 people once. Okay, so you do pick up all 3 cells. You do pick up the 1,000. You do pick up the 2,500. You do pick up the 2,000. Add those up, you get the 5,500, and that goes in the top. Yeah. I think you're getting too paranoid. You're avoiding the 1,000 completely. You want to count the 1,000 people once. Yeah, but you're getting too paranoid. You're avoiding them completely. See, here's the thing. Here's where you do the compensation. If a student had said 3,500 cat owners, right, the row total, and 3,000 dog owners, that left column, right, then you have to subtract the 1,000 because then you'd be double counting, right? Right. So that's the thing. See, so there are 2 ways of doing it. One is to go in, ignore the row and column totals, and grab the 3 entries, right? Grab the 1,000, the 2,500, and the 2,000. Or you could just subtract that 4,500 from 10,000. You can do the subtraction thing, right? The whole thing about the double counting, a student might say the 3,500 cat owners plus the 3,000 dog owners, but wait, then I'd be double counting the double owners, right? Then you got to subtract the 1,000. Yeah. So they're like 3 ways of doing it. There are 3 ways of doing it. Add those 3 cells in the table, subtract that third one from the 10,000. That's how you get the numerator, right? And the third way is what I told you, right? You take the row total and the column total, and then that's where you have to subtract that overlap. But that's when you subtract the overlap if you're working with the row and column totals.
Okay.
There are 3 ways to do it. So if any one of those makes sense, then we're good. Any one of those 3. Any one of those 3. Did you have the homework, the raw problem with you? You have the homework, the table.
Pulling,
the table.
I'm pulling it up right now.
Right.
Okay.
Oh yeah, it helps. It helps to have the table. Otherwise, you don't know time.
Yeah.
Yeah.
I was looking at it not too long ago, but yeah, it helps to have it in front of me right away.
Okay.
Okay. Now I have it.
Good. Okay. Okay. So now again, you have 10,000 in the denominator, right?
Yes.
Okay. So the question is, what goes in the numerator? There are 3
Yes.
ways of doing it. One is to grab the 1,000, the 2,500, and the 2,000. Add them all up because there's no overlap, right? You're just grabbing those 3 individual cell counts and you add them all up, right? So so basically the double cat dog owners, the cat only owners, and the dog only owners, you just add those 3 cell entries up, and that'll get you the 5,500. That's what we want, right? The 5,500.
Wait, there is one thing that's confusing me. I didn't think that we were including the 1,000 because that would include owners of cats and dogs, right?
Excellent question. But here's the thing. The or here is an inclusive or, which means that the and case is okay, right? Like, for example, uh, let's say that you're at college and you're saying, you know what? I might major in math or psychology. I almost did. There's a possibility you could major in both, right? And double major. That's okay.
Yeah.
And you can still say that, oh, I'm thinking of majoring in math or psychology. The thing is, and I was doing this earlier today, you're confusing it with exclusive or, which is soup or salad. You go to a restaurant and they tell you, hey, you can have a free soup or salad, but they're exclusive or. You can only take one of those. So that's a matter of semantics, right? Are we talking about inclusive or exclusive or? In probability theory, we normally mean inclusive or. It's okay to have both.
Okay. How would I be able to tell the difference between the two?
It normally is inclusive or. In probability theory, or is normally inclusive. It's okay to have both. Yeah.
Okay, so in other words, the only way to tell the difference between the two is if it's explicitly mentioned in the question that it is exclusive.
Correct. Because remember, in your stats courses, when I say or, it's assumed to be an inclusive or. It's okay to have both, right? Like I remember early in a pre-cal class, right? I said that the people we let into our party, they can bring beer or food. But hey, if you bring in both, we love you. Come into our party, right? Yeah, yeah. So it's okay to have both. But yeah, you bring up an important point, which is that in stats classes, in probability, when we use the word or, we normally mean it as inclusive. It's assumed to be an inclusive or, which includes the and case. So yeah, I'm glad you mentioned that. So I now see what the problem is. Your issue wasn't the double counting problem. It was defining or as inclusive or, right? Which is an important issue.
Yeah.
Right.
Yeah. Okay. Yeah. I think what threw me off was the way question 4 was written, in that it seemed like I should not include owners of both cats and dogs because I'm subtracting the 10% of adult Fredonians.
Right. I see why that's confusing, because I'm giving you basically the probability of the people who own both, and so you might think, oh, so is that like a bad thing or something? Well, no, because if you're using formulas, you have to know how big the overlap is, right? Like for
Yeah.
example, let's say we want to know the proportion of students at the college who major in math or psychology, right? Well, then I have to know what could help is knowing the number of math majors, the number of psychology majors, but also I need to know the number of both, because otherwise I'm double counting people. So that I have to know that for the purpose of working the formula.
Okay.
Yeah.
Okay.
So it's an important point and a confusing one. I agree.
Okay. Okay. So let me see. So let me see if I can get this right. So now for question 5, I can write dog and cat owners. I was creating this little table where I was adding all the values up.
Right. And you do count the 1,000. You do count the 1,000.
Yeah. Okay. So and then that means that I will have 5,500 in the numerator. And 5,500 divided by 10,000 is 0.55 or 55%. Okay, that makes a lot of sense. Wow, I am ironing this out right now.
Right. It's inclusive as exclusive. Now let me quickly discuss the other two ways you can do it computationally. How do you get that 5,500? Do you remember what I said earlier? What's a faster way you can get 5,500 from that table just by looking at the body of the table in the square? What's a faster way of getting 5,500 besides adding those three numbers in there?
Well, I could subtract the 4,500 from the 10,000.
Right. And for a lot of people, that'll be faster. That 5,500, that also works. It's idea of the complement, right?
Yeah.
Okay.
Yeah, exactly.
Now the third way, and this is where that overlap issue came in. Like remember my example with math and psychology. So in the table, now this is where the row and the column totals come into play. Okay, so we have a total of 3,500 cat owners, right? Like math majors, 3,500 cat owners. We have a total of 3,000 dog owners, right? But wait a minute, we have overlap there. We have to know that there are 1,000 people who own both, right? Because otherwise we're double counting them, right? So you take 3,500 plus 3,000, but then you're double counting the 1,000 people. You got to subtract off 1,000 to make sure you're only single counting them, right? And I remember when you were doing the dice problems, you were very conscientious about circling those cases where you're in danger of double counting, right? So here, the 1,000 is the thing you'd circle.
Hmm. Oh wow, that makes a lot of sense.
Yes. And if you understand all three ways of doing this, then you have you know a lot. If you know the three ways of doing this, then you have a good sense of how to work these tables.
Okay, yeah, that makes a lot of sense. Okay. I hope I didn't dominate the office hour time here, because it looks like a lot of students left.
I think they're actually curious about the discussion.
Okay, all right. Well, if you don't mind, I'll just take a quick look at these. I think I'm almost done.
Okay. In the meantime, I will throw it to the class. Were there any other students who had concerns in the meantime, Chad or? Yeah, maybe they're like me because I like when I was a student, I like to hang around, just listen to what questions people had. Yeah.
Yeah, it helps a lot, I think.
Just to sing it in different ways, you know. Yeah. A lot of often it's just a matter of saying it differently, you know, especially in a stats class. Probability, like just saying it the right way for someone, and you may not get it until the third or fourth time, but yeah, as long as you get it at some point, that's yeah. Yeah.
Yeah, so I guess I was just thinking more about what you said regarding mutually exclusive OR problems versus inclusive OR problems, and
Inclusive versus exclusive, right?
or
Inclusive versus exclusive.
okay,
right?
Or is then let me see. So when you said exclusive, that's the same as the me's, right? The MEES.
No, it's a different meaning. It's a different meaning. When we say exclusive OR, my favorite example is the super salad example, right? Where you can have a free soup or a free salad, but not both. You can't have both a free soup and a free salad. And that's why it's confusing because when people think of the word or, they often think of the super salad example, and that's an exclusive OR. In stats class, our OR is inclusive. So it's more like me saying, again, I'm thinking of majoring in math or psychology, but it's possible I might double major, and that's okay, right? I would still be counted.
Yeah. Okay, and then I was just gonna say when it is exclusive, it can be identified usually in terms of what is physically separable. What I mean by that is if we say we're going to roll a 3 or a 5 and we only have one die, we know that it's only possible to get one or the other.
Okay, so yeah, I can see that you're trying to figure out. So what's the relationship between exclusive OR and mutually exclusive events? You're trying to figure out. Okay, so I will say this because I was thinking about this just now. So what's the relationship? If you have two mutually exclusive events, like I roll a 3 on one die, I roll a 5 on that die, and you agree those are mutually exclusive events. You can't have those both happening on the one die. Then the overlap is empty. There's no overlap. Okay. Which means that you can use the basic probability formula. So what's the probability of rolling a 3 or a 5? Well, it's just 1/6 plus 1/6. And you don't have to subtract anything because both can't happen at the same time. So I will say that that if you have mutually exclusive events, it doesn't matter if you have inclusive or exclusive OR because the overlap is 0 anyway. So let me repeat that. There's an advantage to mutually exclusive events. It doesn't matter if it's an inclusive or exclusive OR because there's no overlap.
Mhm.
Right. So
Okay.
no, yeah, I understood. You're trying to draw the relationship, and that was probably my best example of as to how as to how they could be connected. But generally speaking, you don't really think of them together. But I wanted to give you an example where they were connected.
Hmm.
Okay. Mutual
Okay.
exclusive events have no overlap, so it doesn't matter whether it's exclusive or inclusive or. But other than that,
Okay.
don't worry. Yeah, but I know it's often the case that in math and stats, we use these terms different, different variations on the terms, and we might mix them up. Yeah,
Yeah.
yeah. That's one thing about, and you've seen this before in math classes where we're not good at naming things, right? Like we don't have enough names for things, or we use the same word over and over again when we probably shouldn't. The word normal, like if you are you taking like Calc 2 and Calc 3 later on?
No, I don't believe so.
Okay. Oh, in higher math, they use the word normal way too often. It means a different, like perpendicular or whatever. Yeah.
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 Well, it helps, I think, that you've added quite a few acronyms and other words to the lexicon of math, like the me's and everything.
Well, yeah, just so that you don't have to just that they're accessible, right? Yeah.
Yeah.
Yeah, because you don't want to be scary. I think it makes the statistics less scary if you just have some quick names or acronyms, right? Instead of having to say
Yeah.
mutually exclusive. Actually, disjoint. Disjoint is another short word. Disjoint. Same thing. Disjoint events, mutually exclusive events. Yeah.
Okay. Well, I think this is all very clear to me for now, and I'll be looking forward to our next class on Wednesday.
Oh yes, absolutely, and certainly on Wednesday, feel free to participate and offer your problems that we can work out in detail, right? And then we can do our sort of skim the following Monday. So, okay, because that's the plan, right? I want students to give me the problems they're having trouble with, and we can talk about them intelligently, and then I'll just skim over the various answers for the rest. Yeah.
Yeah, definitely. All right. Have a great rest of your evening.
Okay, you too as well. Yes.
All right.
Any other questions from anyone? Anyone? Okay. Any questions? Okay, so I guess I'll share screen. All right.